Click for IB Biology. Here we're going to be looking at blood pressure, and in particular looking at the graphs associated with taking blood pressures. In the description you'll find a PDF of this presentation that you can use for your own annotation. But also you will find another document which gives the details. It's a table with the details of each of the stages and steps in one of the more complex graphs that I'm about to use, so you can download that for detail as well. When you've covered this work, there's a quick quiz that you can click through to, and I'll add additional channel links to interesting items. Measuring blood pressure is today very, very simple process. There's no longer any need to be relying on equipment like this or like this, which we would find being used by medical professionals, because we can all purchase one of these items here, a simple blood pressure meter that can be plugged in at home, placed on the arm, and from which we can get a fairly reliable measure of our blood pressure. And this blood pressure is normally expressed with two values, and that is that the systolic pressure expressed over the diastolic pressure. So just for explanation, the systolic pressure is the pressure in our artery, usually the arm, which is the pressure generated by the heart during a contraction. So that's the pressure created by the contraction in the pulse. And the diastolic part is the period of relaxation between the pulses of blood, but the blood vessel isn't empty. There's still blood there. So this is the diastolic pressure, is the pressure between the pulses. Let me just put that. So between the pulses. The table here gives some of the values associated with different ages. These are minimum values, normal and maximal. I think these need to be treated with some caution, as a person's blood pressure is subject to many, many different variables, and the idea of normal just only exists for a few people. So let's not overinterpret those or overreact to those. So let's look at the classic graphs of blood pressure. So, as I mentioned, systolic expressed over diastolic. And in this graph here, the systolic pressure is approximately at the peak of the graph here, and the diastolic pressure is at the lowest point on the blue line. Now, the blue line represents the aorta, which is the artery, and the red line represents the left ventricle. So we could perhaps, in terms of a heart diagram, think of this as the left ventricle on this side here, ejecting out blood into the aorta. So the aorta would be here, and this would be the left ventricle. I have removed the trace and pattern for pressure changes in the atria, as these are very complex and affected by a good many factors. In our graph, the x-axis is in time, and notice up here that these are in fractions of seconds. Whereas on the left-hand side, for the dependent variable, our blood pressure is measured. The units for this given here are in millimeters of mercury, which is an old traditional measure and still very, very widely used, although increasingly replaced by measurements in pascals or indeed kilopascals. However, for this purpose, we'll stick with millimeters of mercury. So let me explain the shape of the graph. So we're describing a contraction of the ventricle and the ejection of blood into the aorta. So at A we have, this is the aorta pressure, and this would represent the diastole, the diastolic pressure in the aorta when the heart is in a state of relaxation. And consistent with that in B is the pressure is increasing within the ventricle as blood flows down to and fills up the chamber, but with no contraction of the atria. At this point here, there is a sudden increase in the pressure of the blood in the ventricle. And this, I'll just put this as a note at the base, is where the valves into and out of the left ventricle are all closed. The heart contracts and squeezes a volume of blood that can't escape, and this is called isovolumetric contraction. And I mentioned this previously in the cardiac cycle, but you can see the ventricle pressure rising rapidly up here. Now then we get to this point here, and it's not by coincidence that the red line has now gone above the blue line. So at this point here, what we have is that the pressure in the ventricle is greater than the pressure in the aorta. And that would cause an opening of the semilunar valves. The blood pressure still rises as we eject blood into the aorta. The aorta pressure increases, so the blood is now rushing out into the aorta. So that takes us to point C. So C is the aorta pressure increasing during a pulse. By this point, the heart is entering diastole again. So let's mark that down here, so with a D. So we're entering diastole again, and the pressures fall off. The pressure in the aorta becomes greater than the pressure in the ventricle at this point here. So let's write that in as pressure in the ventricle is greater than pressure in the artery. And of course that is consistent with the second heart sound, which of course we call dup. Now the important thing in terms of structure is that we have the closure of the semilunar valves. And so the blood pulses out into the aorta, reaching its peak here, which we can measure with our blood pressure meters. And the ventricular pressure then falls as the ventricle is now into diastolic phase, the diastole. The details of this are recorded for you in a table so that you can use the PDF and annotate with your own notes using this video for guidance to get the details down about the pressure changes. Let's for a moment think about what we might be presented with in an exam. And so this is a potential example. And the classic thing here could be asked could be, what is the systolic pressure? What is the diastolic pressure? Which is the pressure in the artery, not in the ventricle, because we remember we take it on the arm where the artery is. So we would get those numbers from here and here. Another interesting question that could be asked about this is, how long is a heartbeat? And this would be obtained by measuring the distance between the peaks, almost like the wavelength of this graph. So perhaps we could measure from here to here, although a more precise point might be from F to F, and we would measure that distance like so, and then come up to the graph where we would be expected in an IB exam to make a very careful measurement of that particular time there, which would be the time of a single heartbeat, where the graph repeats itself. Students might like to think about what would this graph look like if instead of the left ventricle and the aorta, the examination question was actually of the right ventricle and the pulmonary artery. How would it appear differently? And that would be worth doing some research on. Once more, a reminder of some of the next videos that you can see in the links here, and also consider subscribing, but in particular, take a look in the description to obtain the materials that support this particular video.